Hello and welcome to my talk on estimating residual risk in Greybox fuzzing. So what is residual risk and why do we need to estimate it? So suppose you've been running your fuzzing campaign for a very long time and you haven't found any bugs. Now you can obviously not say that there are no bugs, but maybe you can get some kind of assurances that if you continue your campaign, you might find a bug. What is the probability that a bug is found if just one more input was generated? Can we estimate that? And so this question is actually highly practical. While we were conducting this research, Fuzzbuzz, a company which offers fuzzing as a service, reached out. And they're currently developing an estimation feature for their product, which directly takes inspiration from our research. And so if we can estimate the probability that a bug is found if one more input was generated, we can also estimate the number of test inputs we would expect to generate before finding a bug. And knowing the average time it takes to generate a test case, we could also estimate the time we expect it takes to find a bug. And so we were exploring an integration of this estimation into AFI++, and we continue to see if we can integrate it together with the AFI++ crew. Most important for practitioners in the security community is, when do we stop fuzzing? And when do we invest our time more economically into developing a better seed corpus or a better fuzz harness? And so if you do fuzzing at a scale like Microsoft or Google, where you have 500 programs and fuzz these 24 hours a day, 7 days a week on 100,000 computers, then you also want to be very economical in assigning this computational resources to your bug finding. You want to maximize the number of bugs found per unit time, and estimating residual risk is contributing directly towards this goal. So there has been previous work on this, particularly for white box fuzzing, but also for black box fuzzing. And we are contributing estimation for Greybox fuzzing, which is now the state of the art. So in black box fuzzing, you could see the estimation of residual risk as a sunrise problem. What is the probability that a bug is found if you generated one more test input? So the question in the sunrise problem is, what is the probability that the sun will rise tomorrow? So the probability can't be zero. You only have positive evidence of the sun rising. There's still some probability weight over negative evidence. The sun will not rise tomorrow. So the first estimator to address this statistically is due to Laplace. So the key idea of Laplace estimator is to essentially assign both events one more observation. So you have observed the sun not rise once, and then compute the proportion of the sun rising based on these updated values. And so what we did is we used these estimators, including Laplace, but there's also one called Turing, and applied it from black box fuzzing and applied it to gray box fuzzing. And what we found is that these estimators severely underestimate, which means the residual risk is estimated to be much less than it actually is. So if a security engineer has some kind of allowable residual risk and would use this estimation to decide when to stop and when the estimated residual risk drops below a certain threshold, then she would stop the campaign substantially earlier, orders of magnitude earlier than she should terminate the campaign. And the reason is Greybox fuzzing is subject to adaptive bias. So in Greybox fuzzing, the probability to expose a bug actually increases with campaign length. The reason is we are adding more inputs to the seed corpus as we fuzz more and more. And essentially the fuzzer gets better and better at discovering errors as the campaign length increases. So how do we deal with this? Earlier, the sunrise problem looks at this as a binary. Either the bug is found or the bug is not found. This doesn't give us enough structure. So the first idea is to add more structure to the problem. simply by considering this as a multinomial distribution. Bug found is one of many events. So suppose we are sampling colored balls from an urn. Each ball represents an input, and the color of that ball represents a coverage element, like a path or a branch that is covered. Now we assign the color black to bug exposing inputs. So now the residual risk is simply the probability that the next ball we draw is black. And discovery probability is the probability that the next ball we draw has a color we have not seen yet, including the color black. And so we can now use estimators of discovery probability as an upper bound on residual risk. So the key idea of good Turing is essentially to take the proportion, the probability to observe a rare species as an estimate of the probability to observe an unseen and even rarer species. So we developed to address this adaptive bias based on this more structured approach. We developed two classes of estimators. The first is called a reset estimators. The key idea is that adaptive bias emerges as we add more seeds to the seed corpus. So we can consider a Greybox campaign essentially as a sequence of black box campaigns, each of which is started when a new seed is added to the corpus. So reset estimators is simply resetting the frequency counts based on which good Turing is computed after the addition of the 8th seed. And then we simply apply the same good Turing estimator. What we do is we essentially removing the weight of the old evidence from our estimate of the species distribution. The second class of estimators is called mean local estimators. And the insight here is that the initial and early seeds have been fuzzed a lot more often than more recent seeds. So they're contributing a lot more evidence to our estimator than the more recent seeds that are more important now. So old seeds contribute more heavily and new seeds not enough to the final estimate. So our idea is to recalibrate that evidence and essentially compute the contribution of each seed to based on their selection probability. So we compute what we call a local estimate, a seed local estimate of that estimator from the local distribution of each seed, and then compute the global estimate using the selection probabilities for each of these seeds. So the results are as follows. So our one reset estimate, so we compute, we set A to 1 and 10. So one reset estimator would reset every time a new seed is added, and a 10 every 10th time a seed is added. And what we find is that we start overestimating residual risk, which in itself is not a problem, because you're overestimating risk, which is usually not a problem. But our mean local estimators perform a lot better. We're always within one order of magnitude away from the actual estimate. So our mean local estimators perform best. We also looked at extrapolation and find that discovery probability and the number of generated test inputs exist within a power law relationship. So in summary, I've explained what residual risk is and why we should estimate it. Particularly, we would like to have some kind of assurance that a fuzzing campaign that finds no bugs might still find bugs in the future. I've talked about some related work and opportunities to prove on this related work. I've explained why estimators from black box fuzzing do not work for Greybox fuzzing. And the reason is the probability to generate an input that exposes a bug actually increases with the length of the fuzzing campaign. A Greybox fuzzer gets better in discovering bugs. I've talked about an opportunity to provide more structure to our method by using the multinomial instead of the binomial distribution and taking corresponding estimators. I've given two classes of estimators called a reset and mean local estimators to tackle adaptive bias. And we found that the mean local estimator performed best. So if you like this kind of work and you're still looking for PhD or postdoc positions, you're welcome to apply in my group at the Max Planck Institute for Security and Privacy in Bochum, Germany. Thank you very much for your attention.